What we're going to do now is look at an example, one that is used quite often actually. This is my own version. These are my own images and so forth, and I'm being a little bit, I've taken my own version of this, but if you do research on this, you will probably find something similar to it. What happened is that there was a researcher who had thousands and thousands of pictures of huskies and thousands of pictures of wolves. And it was basically a training set. It told the algorithm, look, here's a bunch of pictures of huskies and here's a bunch of pictures of wolves. I want you to learn from that. Then I'm going to give you some pictures and you tell me whether it's a wolf or it's a husky. And what happened was they found that this model had 90% accuracy. And this was a deep learning model. And you'll see how what happens here is that it had 90% accuracy, but what it did was it picked out the snow in the background in the pictures of the wolves as the means by which it would differentiate between the husky and the wolf. So is that helpful, the snow in the background? Not really. We were hoping it might look at maybe the hair length or the shape of the skull or or some other thing that if I gave it any picture it would be useful. But what happened here is that the algorithm didn't care what was in the images. It just picked out, it just happened to find out the pictures of the wolves had snow in the background, and it just locked in on that because that was a fact. The pictures of wolves had snow in them all the time, and it used that as a major differentiator between why that picture was a wolf and not a husky. So you can see how you want to know what your model is using to make its decisions so that you don't get this result where it's using snow in the background as a way of making its decision. So this is a great example, I think, of how your model can go south on you. And there are methods. There's some really interesting ways in which you can see how this is happening and unfolding. But I think this is a great example of how deep learning and other black box methods can go south on you. Now we're going to get into a topic called Shapley values. Shapley was a mathematician who invented a way of establishing what features were important in making predictions in the model. I'll get to that in just a little bit, a few things I want to mention. There are other things in Shapley values. There's a thing called LIME, L-I-M-E. It's counterfactual, we've discussed that, but Shapley is one. There's probably at least a half a dozen other methods, but this is a great example and a commonly used one. The other thing I want to mention is that explainability has become its own area of study. Recall in our supervised machine learning in our second video, I mentioned I would bring up something again, and that was dimensionality reduction and feature selection. Those are methods where similar information can be made about how well a feature was used in the prediction, how much it contributed to the predictability. But those are different. Feature selection and dimensionality reduction are different topics. Similar but different. That's a very important distinction. This here with Shapley values is unique and it's quite complex. It's based on game theory, and it's really not worth going into. It's just going to confuse. But the basic concepts are valid as long as you understand that it's separate. What we start out with here, these are features. I'll explain this here. There is a file that's a training set, just like the dogs and cats we saw earlier. But in this one, the class is survive and not survive. And this has to do with the survival of people on the Titanic. There were 2,500 people on the Titanic, roughly, and each person in this spreadsheet has a survive or not survive in it. And the features are things like gender and class and age and a number of others which we won't get into because they really aren't important or they're difficult to kind of understand. And one of the things about the survival was that women and children were first to get on lifeboats, so obviously you would expect them to survive more often. Well, that's what these Shapley values show based on that training data, the 2,500 people with the class of survive or not survive and the features that were used to help make the prediction. You'll notice how these play a role. Gender, I actually had to crop this off. Gender goes way off to the right, um, because gender played a huge role. That feature was very important in the determination of whether someone would or would not survive. You'll see their proportional um, contributions. Class, first, second class, first or second or third class, the higher up you were in class, the earlier you got out. The lowest class was the help, quote unquote, on the lowest deck. Age, of course, kids were first to the lifeboat, so age again played a huge role in determining survivability. And so that's what this is here. This is the global aspect of the predictability based on the Shapley values for this algorithm on this training data. Now let's look at what's called a local interpretation using Shapley values. Here's an individual person. Mary, I don't know her name, but you'll see here we have a bit of a different graphic that shows whether the feature was helpful or not. You'll notice, of course, that the fact she's female was a huge positive factor in her surviving. Her age was somewhat of a factor. You see a smaller number here. Class, she was in third class. So that actually brought down her probability as far as the predictive model was concerned, or the supervised machine learning. This would have reduced her probability. So you can see how these are all basically added up, and you can see their relative proportions as to Mary. So that is essentially Shapley values and explainability, and of course this can be used in any compliance framework to help you understand how the model is reaching its decisions. This is especially important in the fairness in the public policy areas we mentioned when it comes to um, bias, discrimination, and other similar types of ethical issues with machine learning. Well, that does it for explainability, and that does it for our series on machine learning. Thanks for hanging in there. I hope you found this last topic to be engaging. I think it's the most interesting of everything we've gone over in all the videos. Um, we discussed in this series here in explainability, we looked at the different types, the motivations, and we focused on an example of wolves and huskies to see how that really exemplifies how explainability is so very important. And then we finished up with the Shapley values and how those are used to make predictions. I would note there that those are obviously useful in more than just predicting whether someone survived on the Titanic. That can be used for anything. You can explore how your model is working to make it interpretable, to explain it, and of course to just better understand what's going on. So whether it's for discrimination or what have you, ROI, that can be used in that way, of course. But that's it. I would also mention that we can help you explore your machine learning options to reduce cost and risk. And we are really exceptionally placed to do audits of machine learning around explainability because of the various topics we work in are kind of overlapping: privacy, automation, and so forth. So I hope you'll think of us for any of the above. Otherwise, thank you so much for joining, and we look forward to working in a project or having you call us for one reason or another. Happy to chat anytime you like. Thank you again.